All right, now we can start talking about the optimization of a transform. So we want to achieve a transform that is statistically optimal for a group of signals which have a similar random characteristics. And that random characteristic that we are going to consider in this course will be the autocorrelation. So we will assume stationary sequences, stationary signals, and we will assume that we know the autocorrelation, which means spectral characteristics is known. You may ask, what's the idea behind the spectral characteristics, which is related to Fourier transform and the autocorrelation? But actually, if you take the Fourier transform of the autocorrelation, what you will get is called the power spectrum. And the random characteristics of the signal is only second order. We don't expect anything higher order, which is like a Gaussian. What's the second order? It means we have the mean and the variance and the autocorrelation among the samples, and not third order random properties like the skewness or the kurtosis and things like that. Those are something we're not going to talk about. But up to the second order, it means we are talking about the autocorrelation. So the title we can say optimal or optimization of a transform, and it's for second order random processes. The second order thing is quite a good assumption for at least small segments of the image, like the thing that we did for JPEG. We cropped the image into 8x8 blocks and then took the DCT, because inside the 8x8 block, we know that the structure is more or less stationary, and an assumption of autoregressive one model will mostly hold. And when you do this kind of an optimization, what you come up with is also known as the Carhonen-Loewe transform, which is abbreviated as KLT. In different perspectives from different topics, you may come up with the similar idea of an optimization. Sometimes they call it the principal component analysis, and sometimes the Carhonen-Loewe transform and things like sometimes singular value decomposition. So in linear algebra, in other optimization problems, similar ideas will always hold. But for us, we are going to call it or denote it as the Carhonen-Loewe transform. I recommend that you listen to it and pay attention to that, because when you check the literature or if you take a look at the texts about the Carhonen-Loewe transform, what you will usually find will be the implementation method and the formulas for the KLT, which is kind of okay. But the derivation of KLT is also something very interesting, and I find it very intriguing. So we will do that in this hour. The idea is as follows. We have a vector, which is a signal, a finite signal of length, let's say n, okay, capital N length signal vector, which can be represented using some basis in this form: y1, u1. u1 is the first basis, plus y2, u2, plus y3, u3. Of course, it will go all the way up to y sub capital N, u sub capital N. These u's are basis vectors, so their norms are 1, and their inner products with each other are 0. But in the middle somewhere, I will indicate something like y m minus 1 u m minus 1 plus y m u m, plus it will go on up to y n u n. Okay, so capital N is the size, but in the middle I also indicate an M point, because that M point is the place where I will chop off the rest of the items. I will eliminate them, and I will keep only the first M coefficients. I will reconstruct only using the first M coefficients. And I'm going to call this much summation something else. Let's call it X tilde vector. This is too thin. Sorry about that. Let me erase it. Or let me make it a little bit. It must be thick, but I don't know. Whatever. X tilde. Yeah. Now it makes more sense. X tilde. This new vector is therefore an approximation of X with only M samples instead of capital N samples in this, after this transformation. So now what I will do is I want to find the best or the optimum U basis, U sub K basis, such that when I do this operation, the error between X tilde and X is minimized. That is what I will try. So I will define an error vector, let's call it epsilon, which is the vector between X and X tilde. That is the error vector. And we know that that error vector is essentially what we have chopped off, the remaining, which is like maybe J from M plus 1 to capital N, Yj, Uj, right? This is the error that we make. And I want to minimize it. Of course, we cannot minimize vectors. It's in the vectoral form. So let's define a magnitude corresponding to a vector, which is epsilon, not the epsilon vector, but the epsilon value, as expected value of square norm of epsilon vector. Okay, let's call this the square norm of a random vector. Since everything is random, we must put an expected value operator over there, which is, as from the previous line, it can also be indicated as the difference between X and X tilde magnitude square, like this. Now I will write it, the magnitude square of the vector as epsilon transpose epsilon, because this is the square norm, as we know, or norm square of the random vector from linear algebra. And now I will write the last term, epsilon transpose epsilon, as this transpose times this, which is expected value summation from M plus 1 to capital N Yj Uj transpose. Of course, I'm taking the transpose of the first term, and the same term again I will write. But we have to be careful when we are multiplying two summation terms. Not with the transpose, sorry. This time we don't have the transpose. We have to be careful because the indices that we are using are both j's and j from n plus 1 to n. So, but the left-hand side summation j and the right-hand side summation j are different. You may want to use some different indexing terms for those. Because when you make the cross multiplications, they may start confusing things. Now, remember that uj makes an orthonormal basis. Therefore, for different j's, for instance, uj transpose times uk, where k and j are different, will give you 0, nothing. And uj transpose times uj with the same index, when j and k are equal, let's say, will give you 1. So we are going to use that thing. What I'm saying is, maybe I can write in red like this. At the same index uj transpose uj is equal to 1, and at different index uj transpose uk will be equal to 0. So we have a summation at the left hand side and a summation at the right hand side, and we are taking cross products of each with each at the right hand side. But whenever you only hit the same index, it makes 1, and for all the other cross multiplications, it makes 0. And that would make this thing to be equal to only a single summation, like j from m plus 1 up to n, yj square. Because when the j of uj transpose and the j of uj are the same, then their coefficients, which are yj and yj, will be multiplied, and they make yj square times 1, and that's it. You can think of it like this, writing like this. But this step is critical. Please try to understand. It's only because uj vectors are orthonormal. Their cross products are all zeros, except when it multiplies the same index. And summation and expected value are both linear operators that can be interchanged at this point. So I will say j from m plus 1 to n, expected value of yj square. Okay, we can write it like this. Now, this is something that we want to minimize, and the minimization will also continue like this. Let us focus to this term for a j between m plus 1 and n. And what is it? How can I express that one? I will take that one first. Then I will sum them up and then optimize, of course. But what is expected value of yj square is the question that I want to resolve now. That's equal to expected value of uj transpose x and x transpose uj. Now you may ask, where did this come from? Why did I write it? It's from here. Let's come back. What is yj? So that what is yj square and what is the expected value of yj square? So maybe we should start from what is yj, which is a y here. For instance, let's think of this y3. How do we find y3 here? We find y3 as, I will solve it here, y3 is equal to the inner product of x and u3. Do you remember that in linear algebra, we just make the projections onto the basis to find the coefficients? So in order to find the coefficient y3, I have to project x onto u3. That's how much y3 I have. You may think of 2 or 3 dimensional linear algebra to visualize that this works. We have mentioned about this before. And it can be written as x transpose u3, which is the inner product, or u3 transpose x. You can also write it like this. Both of them are equivalent inner product terms. So y3 is x transpose U3 or U transpose X, U3 transpose X. So Yj is Uj transpose X or X transpose Uj. So I'm writing Yj times Yj here. But I have to be smart enough to make sure that the multiplication is in this order. So I don't, for instance, write it as X transpose Uj times Uj transpose X. I don't do it because if I do it that way, Uj's will be in the center of the multiplication and they cannot be taken out of the expected value from the central point. But if I write it like this, then Uj transpose at the left-hand side can be taken out of the expectation because it's not random. It is the transform. And the other Uj can be taken out of the expected value operator from the right-hand side. What I mean is this. This is equal to Uj transpose expected value X times X transpose times Uj. Because Uj's are not random, so we don't need the expected operator, expectation operator. But X is the random signal here, or the vector. So we keep it inside the expectation operator. And here we see something nice. This is the autocorrelation matrix. Expected value X transpose is a matrix, and that matrix is the autocorrelation matrix. So we are going to use it. Therefore, our optimization will have a term, will have terms inside it, which is related to or as a function of the autocorrelation of X. It means that we need to know the autocorrelation of our signal for the optimization. We will need it. It's here. Let's write everything as, therefore, Uj transpose Rx Uj. This is expected value of Yj square, one term. Now, we have the summation term. So I will go here for the summation and write it like this. Summation j from m+1 to capital N. Inside it is Uj transpose Rx Uj. Okay, that is the thing that I want to minimize, epsilon. So I will minimize epsilon, but there's a condition with constraint. The constraint is that Uj's will form an orthonormal set. So, for instance, Uj transpose Uj must be equal to 1. Because if you don't put this constraint, you notice that I will erase, but I want to show you now. This part and this part contains Uj terms. And this is a positive semi-definite matrix. Uj transpose from the left-hand side, Uj from the right-hand side, and in between you have a matrix. It will definitely give you something positive, regardless of the values of Rx. Rx could be any matrix, any real matrix. But this thing is positive. And the minimum that it can attain, therefore, is 0. And you can say that we can have 0 by saying that Uj is a 0 vector. Okay, that's how you can minimize. You can think of minimization. But with this constraint, we don't allow you to take Uj is equal to 0. It's not allowed. Okay, that is the constraint which disables the choice of Uj is equal to 0. So Uj is not equal to 0, but because of this constraint. And the constraint optimization, I'm sorry, let's have this pen. This minimization comes up with the so-called Lagrange multiplier technique that you may have seen or remember from freshman calculus courses. how do we minimize things? By taking the derivative and equating to 0 to find the extreme points. It can be the minimum or the maximum. But with the Lagrange multiplier technique, we take the derivative of a different term that also includes the constraint. And that term is like this. I'm going to call it epsilon prime. Epsilon prime is equal to epsilon plus the constraint for all uj to be equal to 1. And in order to enforce that uj is equal to 1, I'm going to use this expression. 1 minus uj transpose uj, I want to make 0. And I don't put uj transpose uj minus 1 because this term, epsilon, is already trying to reduce the values of uj. So when you reduce the value of uj, 1 minus uj transpose uj, here, this part starts becoming positive already. And the minimum that I can attain is by increasing their values and making them to have a norm of 1. So this is how I construct the Lagrange multiplier. Let me write the Lagrange multiplier again. This time I want to write the epsilon expression 2, j from m plus 1 to n. Maybe I can write everything here inside the same summation, like uj transpose rx uj plus lambda j 1 minus uj transpose uj. Okay, this is epsilon prime. Epsilon prime. And I want to take the derivative of epsilon prime with respect to what and equate to 0. The partial derivative of epsilon prime I want to take, and I want to equate to 0. But what's the partial derivative with respect to? The respect to part is the thing that you're trying to optimize. What is the thing that we are optimizing here? We shouldn't forget that. Sometimes we do a lot of algebra, so we forget what we are doing. What is the thing that we are trying to optimize? We are trying to optimize uj, the basis coefficients. We are trying to construct our transform, our basis. So we are going to do it like this. It's the partial derivative of epsilon prime with respect to uj vector. So it's the derivative of a scalar with respect to a vector. That's a problem, you may think of it, and equate to 0 for all j from m plus 1 all the way up to capital M. But I can choose m to be anything, so this is actually valid for all j from 1 to m, actually, because I didn't specify what m could be. M could be just anything. All right, so this is equal to 0. So I need to take the derivative of this and take the partial derivative with respect to, sorry, uj. What is it? You may not really remember from vector calculus how to handle these things, but I can tell you that they are quite similar to the normal scalar derivatives. For example, here we have uj transpose and uj. So it's like uj square. And what is the derivative of uj square with respect to uj? And that is 2uj, right? And here, that's what I will have. For the specific choice of j, it will give me 2rx uj from here, okay, from this part. How about the other one? I have lambda j in parentheses 1 minus uj square again. So what's the derivative of it? It is again 2uj with a negative sign and multiplied by lambda, and that's it. It's not a plus because of the negative sign. It's a minus 2 lambda j uj. This is what the derivative will give me. This is the derivative. And I get rid of the summation because for only one j sample, I'm taking the derivative. All the other j's with respect to that partial derivative will give you 0. So this is the derivative. Delta epsilon prime over delta uj is this. And I equate to 0. Okay. And this is equal to 0 tells me that I can put one of the equations, the negative one, to the right-hand side of the equation. 2rx uj is equal to 2 lambda j uj. 2's will cancel, and I will have rx uj is equal to lambda j uj. A student who is not aware of vector calculus and things like that may tell us that we can cancel out the uj's and that will give me rx is equal to lambda j, which is of course incorrect because rx is a matrix. It's an n by n matrix and lambda j is a scalar. So they are certainly not equal to one another. You have to solve for this. Solve for this in terms of uj. You have to solve for what is uj. And what's the solution of this equation? Rx matrix times uj vector is equal to lambda j scalar times uj vector. So what is uj? This is a question that I'm asking you, and I'm giving you a few seconds so that you may tell me or type if you wish, but you can tell me. We are not a lot of people right now. Any suggestions? What is uj in this equation? Nobody remembers, no? If you don't remember, just please at least say that you don't remember or you don't know, so that I will know that you're listening, but you don't know the answer. Otherwise, I may assume that you're not even listening. The question again here is, what is uj? Nobody? All right. It's interesting. Nobody is even saying anything like, I don't know, or something like that. You know, thank you. I don't know. That's a good answer. You may or may not remember, but I, at least at this point, want to see that kind of a feedback. Okay. But you may remember this. Okay, you don't know what is uj here, but do you remember anything like this? A times x is equal to lambda x. So what is x and what is lambda from here? This kind of an equation. Because the right-hand side is the same as this one with different indices, which may be confusing to you. But when you look at this new equation, you can realize that this is actually an eigenvalue, eigenvector decomposition. So x is an eigenvector of A and lambda is an eigenvalue of A. The solution to this equation is that. So I will say that uj is an eigenvector of Rx and lambda j is an eigen, sorry, it's not an eigenvector, of course, it's an eigenvalue. Eigenvalue of Rx. Okay, this is an eigenvector eigenvalue decomposition formula. And all the things that you will find on the literature, in the literature or on the web page is regarding this Karl-Lewis transform KLT will start from here. They will say that the basis vectors are eigenvectors of the autocorrelation matrix Rx. They start from here, but actually it comes from these steps of optimization. We minimize the error like this from the top, and one by one we proceed and found out that the optimization gives us this formula. The basis vectors are eigenvectors. But we are not finished over there, because we have to say which uj is u1, which uj is u2, which is u3. How many eigenvectors do I have for a capital N by capital N Rx matrix? We have capital N many eigenvectors. So which one of them is the first eigenvector, which is the first basis? Which one is the second? Which one is the last? That is something that we have to find out too. But for that, we have to start from here. I will take this and carry it all the way here. I will write it again because we cannot see it altogether right now. The thing that we were trying to minimize, the epsilon, what was it equal to? It was from m plus 1 to n uj transpose Rx uj. This was epsilon, remember that? And now look at here. Rx uj is equal to lambda j uj. So this is lambda j uj, which means epsilon is equal to summation j from m plus 1 to n uj transpose, let me write it, uj transpose lambda j uj. But lambda j is just a scalar, and we have therefore lambda j times uj transpose times uj. What is uj transpose times uj? For every j, it is 1. So this is the same as writing it like m plus 1 to n lambda j only times 1. Now, therefore, the error that we make by cropping from the point of m is the summation of all the eigenvalues from m plus 1 to n. How can we minimize this? The minimization gave us a formula. Rx uj is equal to lambda j uj. That's the formula to develop what is uj. But how to order them was left unknown. So we are trying to do it now. The autocorrelation matrix is a positive semi-definite matrix, and its eigenvalues are always positive. Okay, they are never negative. So we are adding up some positive eigenvalues, and we want to make them as small as possible. So let's do it. Suppose that the eigenvalues are these things, these numbers that are expressed on the axis of, let's say, j. Instead of that, why don't we just order them in a descending order like this? So the eigenvalues become smaller and smaller. And whatever the m is, this is m, everything from m plus 1 to capital N is the summation of those small eigen values. So instead of keeping those eigenvalues as randomly distributed, let's order them in a descending order. And therefore, the sum of lambda j would be minimum. because they are the smallest at the tail. And wherever you choose m, it may be towards a little bit left or to the right. Whatever left would be still the minimum summation for lambda j, because they are the smaller ones around the tails. So we have to sort the lambda j's in a descending order. But when you're sorting lambda j's, remember that every lambda j is attached to a uj. Every eigenvalue is attached to an eigenvector. So they go together. When you are sorting lambda j's, you also automatically sort together with the lambda j. You are sorting the uj's. That's how you decide which uj is u1 and which uj is u2. So uj with the largest eigenvalue will be u1, and uj with the second largest eigenvalue will be u2, etc. It goes on like this, and the uj with the smallest eigenvalue, lambda j, will be the last one, u sub capital N. You will choose it that way. That's how we order the basis vectors, uj's, according to the corresponding eigenvalue. We are sorting them. Okay, and this is called the Carnot-Loewe transform construction. But of course, we did not construct the Carnot-Loewe transform. We constructed the Carnot-Loewe basis. Let me put it like this. We are making a U matrix with U1, U2, U3, all the way up to U sub capital N, like this, where of course this will have a lambda 1, this will have a lambda 2, correspond to a lambda 2, this would correspond to a lambda 3, and lambda 1 is greater than or equal to lambda 2, greater than or equal to lambda 3, etc. And this is lambda sub n, which is the smallest of the eigenvalues. We make this an n by n basis matrix. The transform that we have is essentially the inverse of it, inverse of the basis representation. This is the basis, U is the basis, T is the transform. T is the KLT matrix. So if you have X as the input vector, how do you find the KLT of X? You say that Y is equal to capital T times X, and therefore Y is the Carnot-Loewe transform of X. And we know how to construct T. We construct it from U, and we know how to construct U. U are the eigenvectors of the autocorrelation of X. This is telling us a few things. First of all, KLT is therefore not a universal transform. We don't have a KLT matrix with some numerical values. You can evaluate your own KLT or construct your own KLT matrix depending on what kind of an autocorrelation Rx you have in your signal. If you have a different autocorrelation Rx, then it will give you different eigenvectors as U, and its inverse will be, of course, different. And that non-universal behavior is unfortunately avoiding or prohibiting us to use Carnot-Loewe transform, KLT, in, for example, compression in JPEG. In JPEG, we don't use KLT, we use DCT, because DCT is known, it's there. KLT, it depends on your signal. So KLT is a signal-dependent transformation. If you have a lot of data with the same autocorrelation, it may be wise for you to first construct the KLT and then find the KLT and then use it for the compression. Because the decoder needs to know what your KLT is. What kind of KLT did you develop? I cannot invert a KLT because I don't know what it is, what your KLT is. You have to first tell me For example, if it is an 8 by 8 KLT that you're using, it corresponds to 64 coefficients. So first you have to tell me what those 64 numbers are, which requires some bandwidth. But if you're going to use it for thousands or millions of 8 by 8 images, then it may be good. First transmit your KLT and then use it for compression. It may be beneficial. So the question that I asked during DCT is more related to this. If the autocorrelation is like this, variance 1 rho square rho to the n minus 1 and rho 1 rho all the way up to rho to the n minus 2, rho square rho 1 all the way up to rho to the n minus 3. This also goes up to rho to the n minus 1. This goes up to rho to the n minus 2. This is rho to the n minus 3. And the diagonals are all 1s. This autocorrelation matrix structure is an AR1 structure with a correlation coefficient of rho. And as rho goes to 1, as rho goes to 1, the KLT, the corresponding KLT goes to DCT, discrete cosine transform. And it comes from actually this kind of a structure of a rho. Or an autocorrelation matrix containing rho terms. People can, a good mathematician can work on trying to find the eigenvectors of this, and as rho approaches to 1, the eigenvectors approach to a harmonic cosine structure. Okay. It may be difficult for a non-mathematician like me, or like probably many of us, to do it that way, but what I can say is that in a future examination, like the final take-home, I may tell that rho is equal to 0.9, for example. So you find an Rx, then find the eigenvectors of this with the eigenvalues and sort them in a corresponding order. So find the Carnot-Liouville transform from here and show or plot the eigen, sorry, basis image, not eigen, I'm sorry. Plot basis images. How do you plot the basis image? You take the first row of the T transformation matrix and take the outer product with itself. And the first and the second outer product is a new basis image. The first and the third row will give you, outer product will give you the other basis image. For an 8 by 8 case, of course, 8 by 8 case, show the basis images. You will notice that those basis images somewhat resemble the basis images of discrete cosine transform, DCT basis images. And these ones will look quite close to one another. But I would like you to make some MATLAB or something like that implementations to show that for rho is equal to 0.9, for instance, things work well. KLT and DCT are more or less the same. That's why we're not using KLT, but we are using DCT. Now, finally, for the last few minutes, I want to talk a little bit about what these eigenvalues physically mean in an autocorrelation matrix, and how can we relate it to a scatter plot that I have shown you before. What was the scatter plot? The scatter plot was this. X and Y are the values of a vector let's say V vector is X and Y with a strong correlation. How was it? It was like this, okay? An ellipse along a direction. That direction is, of course, clearly 45 degrees for normal stationary signals, although it doesn't look like 45 degrees here. Sorry about that. This is called a scatter plot. And the scatter plot also indicates the correlation structure. And I can also see the eigenvalues here and the eigenvectors. The eigenvectors are clearly the 45 degrees rotated axis of this one, okay? And the eigenvalues are essentially the thickness corresponds to the smaller eigenvalue. There are two eigenvalues of a 2 by 2 correlation. And this distance from here to here is the larger eigenvalue. So this is lambda 1 and this is lambda 2. Sorry, it's just the opposite actually, because we say that the larger one is the first eigenvalue. Lambda 1 is the longer one. Lambda 2 is the smaller thickness. These thicknesses indicate eigenvalues. So in Cardinal-Loewe transform, we are trying to find the principal axis where the most variation is shown, corresponding to a variation of lambda 1, for example. That is the energy variation of the signal along that direction. And anything which is orthogonal to that would be the minor axis in 2 dimensions. But let's assume you have 3 dimensions. By the way, the amount of error that you make by eliminating the second axis would be equal to lambda 2. Okay, lambda 2 much error is what you will make. That's the thickness that you eliminate. Therefore, that's the error that you make. Let's think of something in 3 dimensions. Then in 3 dimensions, the situation is like a meatball, okay? A flat meatball. It has one major axis, which is the height of the meatball. And then there is the width of the meatball as well, like my hand, okay, my hand shape. So this size is lambda 1. This width is lambda 2. And this thickness is lambda 3. They are all orthogonal to one another. So whatever the original orientation of my hand was, I have to rotate it in such a way that the first direction shows the highest variation, which is the height of my hand. And the second, which is orthogonal to the first, will be the width of my hand. And the third, which is orthogonal to both of them, would correspond to the thickness of my hand. So the scatter plot would be 3-dimensional hand-shaped thing, for example. The narrower those ellipses are, if the thickness of my hand is, for example, 0, then the better compression efficiency I will have, because by eliminating this thickness direction completely, I don't make any mistakes. Or if the width of my hand is very narrow, okay, then that would also mean that the amount of error by eliminating 2 coefficients, the minimum and the one after that, I will still make smaller mistakes. So we want our signal to have a scatter plot that is as narrow as possible. We don't want spherical or circular type shapes where compression is very difficult. But of course, they are the inputs, and sometimes the input is like that. It means the input is not very much compressible efficiently. So what have we seen? We have seen that these things are equivalent to one another. Max eigenvalue of Rx is the direction, which is the principal component size or the energy of that component. Because the energy and the eigenvalues are corresponding to the same things. So I may ask you to optimize in several ways. I may ask you to optimize with a rotation such that one of the rotation axes shows the minimum variation. That's one way of asking the question. I can ask you to find the minimum eigenvector, eigenvalue, or the maximum eigenvalue, make an eigenvector decomposition, which is the KLT way of doing things. I can ask you to minimize the energy of the coefficient corresponding to one of the bases. They are all the same things, same question being asked in different ways. So in the final examination, I will ask you, I will give you a normal example autocorrelation matrix. I will provide that autocorrelation matrix to you, or I can give you some data from which you can approximate the autocorrelation using autocorrelation approximation techniques. You may have to research for that. Or I can give you just the autocorrelation matrix, give it to you. And I can ask you to make optimization in several ways like these. From this perspective, from this perspective, or from this perspective, you make the optimization and you will see that, you will observe numerically that they correspond to the same optimization, or to the same transformation, the same optimal transform. There is only one optimal transform statistically, but there are many ways to look at it, many ways to visualize or understand what it really means, like principal axes, rotations, minimization and maximization of eigen values, etc. Okay, so this is what the Karhunen-Loewe transform is all about. And in image processing, there is one other thing where Karhunen-Loewe transform is used, and that is not the compression of images, but template matching and detection of shapes inside images. So we're not using the statistics of images, but we are going to use the image itself. It's like this. Suppose that you have two types of images. One of them is a screwdriver, something like this. No, it's not a screwdriver, it's a key. A key is this, and a screwdriver is this. And suppose that you are working in a factory where on a conveyor belt, these two things are passing, and you have a robotic hand and you want to pick the keys and leave the screwdrivers. How are you going to do that? You can do it like template matching, because you know the template of a screwdriver and you know the template of a key. So is the shape a screwdriver or a key? You have to decide. But how can you decide? They may be here like this, like this, like this. Orientation could be just anything. How can you make a template matching for matching these two shapes, whether it's a key or a screwdriver? There is one way to do it, and that is the normalization of the angle to the right-hand side. And remember that Karhunen-Loewe transform is essentially capable of doing it. It rotates it towards the major axis. What is the major axis of a key? For this example, it is this. And for the screwdriver, it is this. Those are the directions. So let's make it the horizontal direction. Let's rotate the image according to the principal axis. The way to do it is as follows. Inside the object, of course, we have some pixel values. and the background is a different. Of course, there must be a difference between the inside and outside. Now, for the first shape, for example, we take x1 vector, x2 vector, etc. There may be several of these things, xm, let's say, vectors, as x1 and x2 coordinates corresponding to the foreground image, corresponding to the key. So these are the coordinates, x1, x2 coordinates. Of course, there are many of them, m of them. And we come up with x1, x2 couples like this, x1, x2 of 1, and x1, x2 of 2, etc. And x1, x2 of m. We have m of these. From these m, we can estimate a 2 by 2 autocorrelation matrix, which is, let's say, A, B, C, and D. Okay. This autocorrelation, 2 by 2 autocorrelation matrix, is not the autocorrelation of pixel intensities. We are not taking a look at the autocorrelation of the intensities. They are the autocorrelation of the coordinates. It's a different thing. It's a 2 by 2 autocorrelation. This is x1. This is the x2 axis. Then you find the eigen decomposition, and u1, which is the major axis, would correspond to this direction. And of course, u2 will correspond to the one that is orthogonal to that. Okay, two orthogonal vectors. And we make the rotation according to these two axes. We rotate them back, and it's going to give me an image like this. But I forgot to mention that I must first subtract the mean, so that the center here is first moved to become x1 and x2, like this. This is the mean of your x1, x2 things. So x1 and x2 are first showing the mean, and then afterwards we find the directions and rotate. After the rotation, this is what you will have. Now, since it is aligned horizontally, I can make template matching with another key shape, and I can make template matching with a screwdriver shape, and it will match better to the key shape. So I will decide that this is a key. And you can also do the same to the other one, where the center may be somewhere here. And after rotation, it will be looking like maybe this, okay? And you can compare with a horizontal screwdriver by template matching and say that this is a screwdriver, not a key. It's possible that it could also be rotated like this, okay? Either of them. But why don't you just make template matching with both, and then decide for asymmetric shapes? You can also decide by comparing both of the horizontal alternatives and make template matching. So in black and white images, or foreground versus background images, the way to do template matching is first by applying something like Karun and Loewe transform to the coordinates of the image, not to the autocorrelation of the image, but the coordinates. The coordinates are now like the autocorrelation shape. It's like that ellipse, you remember. Now we don't have the ellipse, but we have the shape itself. So we rotate it using this idea first, and then apply template matching. And believe it or not, there are a lot of people in the industry who are using image processing for doing these recognition things who are not even aware of this kind of a methodology. And that's a shame. They are trying to, for example, apply deep learning and things like that, which is okay for modern technologies, but it's an overkill. Probably that deep learning machine will require a high capacity computer, but with this kind of a rotation, it's just 2x2 things that you can even implement without a computer. It's just with very weak ARM processors and things like that, maybe Arduino, even simpler. So you must be aware of the techniques that can be used in image processing, and this is one of them. This may be more related to image processing than all the things that we have seen, which are more related to compression or representation of images. But this one is essentially at the heart of, at the core of image processing, as we see. Okay. I want to stop at this point, but I may give you the microphone if you have any questions. So do you have any questions?
Hocam.
Yes.
Duyabiliyor musunuz beni?
Evet.
Şey soracaktım hocam, ders dışında projeyle ilgili konuyu belirlemekte biraz sıkıntı çekiyorum da sizin
Okay. That's a good question.
varsa.
Okay, that's a good question, but maybe I should stop the recording because the course is over, and I will answer, or we may discuss afterwards. So I stop now.